We're down to communication and network security. This is essentially Net Plus. So a quick summary of basically Net Plus level protocols and networks. So when you communicate over a network, there are three types of communication. There's simplex, where you just send it one way only, like FM radio. You broadcast it from the station, people can receive it. There is no way to send data back to the server. That's simplex. Half duplex is where you send and receive, but not both at once. This is like the walkie-talkies, where you say, "Are you there? Over." And then they say, "Yes, I'm here, over." And they keep saying over, so you know it's your turn to talk, because only one of you can talk at a time. And most things nowadays are full duplex, where you can send and receive simultaneously, like a telephone. Both people can be talking, and the sound will transmit just like it would through normal air. Baseband is where the entire frequency range is dedicated to one signal, like Ethernet. You have a cable plugging into your computer, going into a switch, and you have full use of that cable. You're not sharing it with anybody else. Then there's broadband, where you have multiple channels, like FM radio. You have a dial, you can tune into different channels. Many channels are all sending things through the same physical space, the same electromagnetic transmissions. Then there's analog signals, where you send things like a smooth variation, like when you talk in a room, people can hear you, they're hearing analog motion of the air. It's not digitized. The problem is the signal degrades over distance, and when you record it and repeat it, it is degraded every time you do that, and vinyl records are this way. Digital signals digitize the signal into a series of zeros and ones, and now you can transmit and repeat it with no loss of accuracy, because you can calculate error detection codes like hashes, and if something is wrong, you can retransmit it until the hash comes out right. So you can essentially have any number of perfect copies of a digital signal, and you can transmit it with complete perfection anywhere. As long as you have a channel that has some degree of successful transmission, you can eventually transmit it with 100% accuracy. Local area networks are within a building, metropolitan within a city, wide area network, anything really big, typically cities, states, or countries. Global area network, another term, and personal area network, a more modern term for the devices you carry on your body. Things like your earpiece and your phone and my Apple Watch and really my laptop, they're all connected by Bluetooth. So I can do things like log into my laptop by having my phone nearby, which is logged in, things like that. That's a personal area network. So the internet is the global collection of all the networks running TCP/IP, which is the protocol they almost all use. Intranet is a privately owned network, and an extranet connects private intranets, so you may have a connection to a business partner, so you can ship things to them through a private network not exposed to the public internet. Circuit switching networks are what the phone lines used to be decades ago. You would get one piece of wire just for you to use. And if you're making a long distance call, you'd have to wait for a circuit to be available. Now everything is packet switched. So every transmission is broken up into little data packets. They move like cars on a freeway. So the same line is carrying many packets from many different sources and destinations, just like a freeway, and they're each being routed and switched to find their right traffic. Therefore, it's cheaper than circuit switching. The same cable can carry many different kinds of traffic. Of course, it has some total bandwidth maximum, and you aren't going to exceed that, but if the individual users don't need the full bandwidth, they can share it. So you have an issue of quality of service. There may be some traffic that is higher priority than other traffic. For example, if you have voice over IP traffic for sound for telephones, you really don't want that to be delayed by even 50 milliseconds because that'll break the sound. Whereas packets to build something like email or a web page, they could be delayed by half a second and you wouldn't really care. So you use quality of service to specify what priority the packet should get going over a shared channel. And you have a layered design. This is a very important concept, appears in many places in computing. So you can define what each piece of hardware should do and software, and you can plug it in with other brands of hardware and software as long as they all obey the standards. That's the idea. So there's two popular network models, the OSA model and the TCP/IP model. And there's network stacks, which is a series of protocols used, like TCP/IP is the most common stack. So the OSI model is the one that came from Europe. In theory, it's what's going on. 7 layers: physical, data link, network, transport, session, presentation, and application. And you need to memorize this. And here's some mnemonics. Here, please do not throw sausage pizza away. Goes one way. All people seem to need data processing. Goes the other way. You should memorize one of these and know what the various layers are. So layer 1 is physical. The data is sent in bits. This is things like Ethernet cables, radio waves, fiber optic cables, and hubs, repeaters, and cables operate at this level. Hubs and repeaters are devices that might look like switches, but they're not smart. They don't read any address or address anything. They simply take in a signal and then repeat it out the other ports. So all they do is transmit it to everybody who isn't the one that sent it to them. That's what hubs do. Repeaters just make it stronger again so it can go down a longer length of cable again. All right, those are devices that don't interpret the data at all. They just repeat the data out. Then at the data link layer, you have your first layer of addressing. Now you have MAC addresses, which uniquely identify the devices on your local area network. And now your Ethernet card can tell if data gets is intended for your machine or not. And unless you put it in promiscuous mode, it will only accept frames that come in with your MAC address on. And you have switches and bridges, which maintain internal tables so they know which MAC addresses are out which ports. And they will only send the data out the correct port to reach the device you're talking to. So in principle, there's two layers here: media access control connecting to layer 1 and logical link control connecting to layer 3 within the layer 2. And layer 3 is where you have IP addresses. So this is what goes through routers, and this is what goes over large geographic distances to find the device you're talking to. So if you're reading Gmail, this goes off on the worldwide internet, and it goes through routers to find Google from wherever you are. That's what IP addresses do. They can move to the physical location of the other device you're trying to talk to. And the transport layer breaks things up into segments using UDP and TCP protocols. Usually there are other protocols, but these are the most common ones. Uses port numbers, which are 65,536 UDP ports and another 65,536 TCP ports. TCP is reliable. It has a handshake. It has a mark in each packet, in each you call them packets at this, like IP packet frames, segments. You call them segments at this layer. It marks each segment with a number so it can reassemble them in order. So you can send something like an image that might be 100 segments, and it will rearrange them in the right order. And it also will notice if it didn't get one and require a retransmission. So that's why it's reliable. TCP will detect if data is missing and request a retransmission. So if it gets all the retransmissions, it will in fact have the complete data at the other end. UDP is unreliable. It just sends things with at best effort delivery, but it does not get any response from the other end saying whether they got there and requesting a retransmission. So if something is lost, it's just lost. And it's used for things like a streaming security camera where you just want to see what's happening at that camera right now. And if there's a glitch and some static in the line, forget about it. Don't try to fix it. Just show me the next packet so I see what's going on now, because all I care about is real-time information. I don't really care about it being 100% accurate or fixing mistakes later. And there's session layer where you have requests. Something has been established here indicating something special about this connection, like, for example, you've logged in. So now we've got a session. I know who you are. That distinguishes you from other people. All right. And then presentation. This is what converts data into a way that's useful to the end user, taking bytes and decoding them to become ASCII or image formats, encryption or compression. This is what takes data that has been delivered through things like TCP and rearranges that data in a form that's useful to the end user. And layer 7 is where human readable data is. This is where most normal people live. They are not even aware of all those other layers. You open up your browser, you read your email, you watch a YouTube video, all at this layer. Everything makes sense. And you know, normal users just know sort of vaguely that somehow or other it's sent over the internet, but exactly the translation it passes through to get down to the internet and the various addresses it uses are all not visible. All right. So let's try a Kahoot. I've got them here. Let me just adjust this window. So hopefully you'll be able to see the magic Kahoot number. And I want 4A, which is here. All right. And I'll see if the number comes through. Ah, looks okay. Good. A little Space Invader. The name. That's good. It must be a Unicode character, I guess. That's right, the Tesla bots are supposed to be out there. Optimus bots. He demonstrated them, but they were fake. They were just controlled by humans. But they tried to trick the attendees into thinking they were running on AI when they weren't. Typical Tesla gag. Anyway. All right. All right. So what kind of transmission goes through an Ethernet cable? Yep, baseband. That's when you have all the bandwidth used for one channel. All right. All right, which OSI layer uses MAC addresses? Okay, layer 2, that's where the MAC addresses are. Which layer has hubs? Hubs are not very common anymore. They've mostly been replaced by switches, but if you have one, this is where it operates. Well, yeah, Akron, what happened is the time is set too high. This is set, the music is chosen by the time interval, and it should be 20 seconds, but these are set to 60 seconds, probably because I changed something in the early days of doing this, forgot to change it back. Anyway, that's layer 1. Hubs are completely stupid. They just transmit like a cable without reading any addresses at all. That's layer 1. All right, and what layer includes network file shares? That's up here. We normally put that at layer 5, a session layer. You typically have to log in somehow to access a network file share. It's beyond the first 4 layers, which are just communicating with the right piece of software on the right device. All right. Space Invader will have to tell me who they are if they want the points. But by the way, I encourage you to check your scores. If you've been winning the Kahoots and not getting your points, it might be that we don't know who you are. There are a few students like that, using some kind of fake name we couldn't figure out. So be aware of that. All right, so here's the TCP/IP model we just talked about, and here's the OSI model. The TCP/IP model maps to it pretty much. You call the lower 2 layers network access, internet instead of network. Transport remains the same, and everything above it you call application. This is more the way things are really built. The OSI model is sort of a theoretical model in principle, what's going on, but in practice, you typically have something like a web browser that does all of these things in one program, so separating them is not really meaningful. Now, these layers are meaningful. These 3 have real addresses attached to them, MAC addresses, IP addresses, and TCP ports. So those are very real, so you have to pretty much have them. Here they mix it with the physical, which is arbitrary. But that's the idea. TCP/IP model probably is closer to the real hardware you would buy. So the lower layer combines 1 and 2. This includes cable and the network interface card, and therefore uses MAC addresses. The internet layer is OSI layer 3, so it has IP addresses and routing. So just like before, this is the thing that transports your packets a large distance to find the geographical location of the thing you're talking to. And a transport layer is what chooses which process on the server you're trying to reach. Once you reach a server, it might be offering several services, and the TCP or UDP port is how you determine which service you're talking to. 80 for HTTP, 4 to 43 for HTTPS, and so on. So the application layer is everything above it, like I say, like a web browser. This is what takes the packets that have come in and does all the things above it. Decides if you need to log in, decides if something has to be decrypted or reformatted, and presents it to the user so they can see it and understand it. So encapsulation is fundamentally used everywhere here. This is like putting a letter in an envelope and addressing it. Everything is encapsulated. So your TCP segment is a piece of something like an image you're trying to send over the internet. That's encapsulated in a layer 3 packet. That's encapsulated in a layer 2 frame, which is sent over the wire as bits. So everything has 3 addresses, which I found very confusing at first. You get used to it, though. The frame is addressed with a MAC address to find the right device on your local area network. The packet is addressed with an IP address to find the right computer in the geography of the world. And the segment is used to determine what piece of data this is, how this fits with other pieces of data to be presented to the application above. So, and the port number here tells it which process you want to talk to on the server. So it's really not that different than a normal mail address where you have zip code, city, and then a street address. All different layers of the addressing. So SPF 10 is one way to remember this. Segment, packet, frame, 1 and 0 bits. So at the bottom you have bits, that's the physical layer. Then you have frames above that, Ethernet frames with MAC addresses. Then you have IP packets with IP addresses. And then you have TCP segments with port numbers. So that's the way it works. So you can call it decapsulation at the receiving end. You receive bits. You then convert them to frames. You strip the MAC address off the frames, and inside there you find packets with IP addresses. You take those packets and convert them to segments. Then you combine the segments to build the data, using the numbers in them to correctly put them in the right order and request retransmission of the ones that are missing. All right. So the MAC addresses are unique hardware addresses of them. It's burned in at the factory, 48 bits long. When you buy a network card, it has a MAC address in it. All right. And there are addresses that were used sometimes to create IPv6 addresses by using some of these addresses, but that turned out to be a bad idea for privacy and has largely been abandoned. So IP version 4 is what's most commonly used, where you have these 4 numbers going from 0. Each number can go from 0 to 255, and they're separated by dots. And that's really a way to represent a 32-bit binary number, which is what it is. So the IPv4 header looks like this. You have the version here, which would always be 4 for IPv4. Then here you have some flags we'll talk about. I don't need those much. They have time to live. Every time you hop from one router to another, or you wait for more than 1 second in a queue, time to live goes down. So if a packet is set down a routing loop, which can happen, where it just goes around and around in circles, never getting anywhere, it will be discarded after a while. It won't just tie up the internet with lost packets racing around in circles. That's why you need time to live. And you have source and destination address, which are 32-bit fields. So there's fragmentation. This is a pretty terrible idea, but it was necessary decades ago when there was another protocol in use called circle something. The name may come to me, but there's some protocol I've never used, but banks were using it. And the problem with it is it had large packets, like 10 kilobytes. So when you connected that network to an Ethernet network, the single packet of the other network would be like 8 or 10 Ethernet packets. So one thing, rather than refusing to take it and sending a message back saying, I can't handle it, send me smaller packets, which is what would happen now in IP version 6, it would actually fragment the packets. So one IP packet sent from the network with a large frame, the large packet size, would be broken up into multiple packets and retransmitted here. This turned out to be a pretty bad idea. There were a lot of ways to exploit it. There's a tool called Frag Router in Kali that will break all your IP transmissions into little tiny packets moving only like 8 bytes at a time, hoping to fool network malware detectors, like network monitors. Since they never see very much of the incoming data, they can't really add it up and decide whether it's malicious. That's the idea. Anyway, now you use path MTU discovery. You send a large packet, and if it's dropped, you try a lower packet size. That's what happens now in IP version 6. If the paths you have to go through to get to the destination cannot handle large packet sizes, you detect that and lower your packet size until it goes through. So the source, the data sent by the source does not have to be refragmented on the way there at layer 3. IPv6 header is simplified. The addresses are much bigger, 128 bits long, but they got rid of a lot of the useless stuff up here, and now they call this hop limit instead of time to live, because in fact it really only measured the number of routers you hopped through. Nobody's ever had a network where you'd actually wait for a second in a queue, I don't think. So calling it a time live is kind of a misnomer. What it really is a hop limit. All right. So IPv6 addresses are auto-configured. I've had students get confused by this. They say, hey, my machine has got 2 IP version 6 addresses. Now this one has only one, an FE80. The FE80 address is auto-configured every time an interface comes up. That's like a loopback address, like 127.0.0.1. It only works on the local area network, and if you have a public IPv6 network, it will get another IP version 6 address, starting with 2 or 3 for a public address on the same network. It is very common, almost universal in IP version 6 that every interface has multiple addresses, which is not a common thing in IP version 4. Anyway, so the MAC address can be used to construct the host portion of the IP address. In IP version 6, this is the old system. As you see, the Ethernet address here is the MAC address. And if you look here, this ends in 9EB3, which is this, 9EB3. So they used part of the MAC address to determine the IP version 6 address. And like I say, that was a way to get a somewhat unique address, but it turned out to be a poor idea for privacy, because the MAC address never leaves your local area network and uniquely identifies your hardware. So if you were like downloading pirate MP3s, if they could get your MAC address, they'd really have high confidence that they knew who did it. But now, the way modern networks are set up, you only get the IP address, which just indicates the physical location of your machine, and if you turned it off and somebody else came in and booted up, they might get that address. That doesn't really prove who you are. So this was considered a privacy exposure, to take a layer 2 address and include it in a layer 3 address, and I think all modern operating systems no longer do it this way. Anyway, so IP version 6 has created some challenges, but I think we've all kind of got used to it by now. Now it's carrying something like 20 or 30% of all the traffic. A lot of carriers mix IP version 6 and IP version 4 these days. For a while, you could get away with breaking security policies by using IPv6 traffic, but I don't think that's true anymore. You can disable it. Just go into your network properties and turn off IP version 6. And anyway, originally there were classful networks used until 1993 for IP version 4. We had Class A for the first half of the space, and Class B for half of what's left, and Class C for half of what's left, and D and E hardly ever used at all. So that's the A, B, and C networks to determine how big they are, but that was switched in that year, 93. They decided they're running out of addresses, so they wanted to be less wasteful about using them. So instead of just having Class A with 16 million addresses and Class B with 65,000 addresses and Class C with 256 addresses, they wanted to break these into smaller chunks in between them to be less wasteful. So now we use the slash number, /8, 16, and 24, which determines how many ones there are in the network mask. And now you can have a /9 and a /20 and a /26, all these sizes of networks. So you can more accurately tailor the size of the IP network to the size number of machines you really have, being less wasteful. However, all these attempts to extend the life of IP version 4 did hit their limit. Oh, okay, this /20, see, /24 is a Class C. That's got 256 addresses. A /20 has 4 more bits used for hosts, so it is 16 Class Cs. And this, by the way, is what City College uses for the wireless network. We don't want to limit this to only 256 students on the network. They use this, a /20, so you can have 2,000 students on the network. That's all. This is what you do. You cut this. /20 is halfway between the 16 and 24, so it's geometrically halfway between these. It's 16 times 256. That's what it is. All right. And there are private addresses, of course. Anything starting with 10 is private. 172.16 through 172.31, and anything starting 192.168. Those are all private. If you send traffic into a public router to try to reach somebody at this address, your package will just be thrown away. They can't be purchased or assigned to a domain name on the internet or anything. You can use them in private networks, but not on the public internet. They're reserved for this purpose. This has interesting consequences. I've heard of people where one bank labeled all their devices 10 and another bank labeled all their devices 10, and when you merged the bank, there was a huge problem. You have to renumber one whole bank's network. Kind of annoying. Anyway, the kind of thing that's fixed if you move to IP version 6, where there's so many addresses that you don't have to all keep using the same ones. Anyway, let's try 4B. All right. I think 6 is the number that participated last time. All right, so which layer uses segments? Layer 4, TCP segments. All right. Which addresses are 32 bits long? IPv4 to give you the physical location of a computer you're trying to communicate with. All right, what class is this in the old class 4 IPv4 system? That's class C. Up to 128 is A, up to 192 is B, above 192 and above is C. You keep cutting the space in half. So this is in the third group, class C. All right. All right, which addresses are 48 bits long? Yep, that's the MAC address. All right. Well, that's something I've had students say before. The same people keep winning the Kahoots. Well, and it's happening that way today. I'm not sure anything's wrong about that, but that's the way it is. All right. So network address translation, typically used with port address translation. The most common use of this is so many computers can share one internet connection instead of paying for another. So you have one public address you get with your internet service provider, and then you split it up into multiple private addresses. Now, of course, you only get so much total bandwidth, So if you have more machines and they're all downloading things at once, it will be slower. But anyway, you don't have to pay for your own internet connection. Static NAT is an old system where you'd have one private address to one public address that's almost never used. Wait, 96 is, does that mean the addresses can range? 196 through 111? Yes, that looks right. You had 32, no, it's bigger than that. Oh no, 16, that's right, 16, yep, that's right, you've got it. Hey, Corinne, I see your example is correct, or /20. All right. And then there's PoolNAT, a group of public addresses translated one by one to the same number of local addresses. Both of these are weird old techniques. What you mostly have is this. You have one public address out here, 147.144.51.1. Then this machine has a second network card with a private address. So this is your router, typically. It's got two network connections, one to the internet, one to the LAN. Then you have your LAN on a hub or a switch, and everything here has to have a private address on this network, 192.168.1, 101, 102, 103, and it has a gateway here. So if this machine wants to talk to anything on the local area network, it can go directly through the hub or the switch. If it wants to talk to the internet, it has to send it to this machine, which is the gateway out, and that machine has the ability to route packets off onto the real internet. And what it'll do is if all these open, say, web browsers, and they're all running on port 443, for example, it will remap those ports to give them different port numbers out here. So now to be fair, they're all trying to reach servers on 443. They'll be on local addresses like 50,000, local port numbers. But even if they all shows the same local port number, which could happen, this router will change that port number. So from the viewpoint of the internet, there's just one computer with 3 browser windows open, instead of 3 computers down here with browser windows open. That's what it is. All right. So ARP is used to find MAC addresses. For example, if you're here and you want to get on the internet, you have to get to 192.168.1.1, but you're going through a layer 2 network, through a hub or a switch, so you can't address anything by an IP address. You need the MAC address of the router, and you don't know it. It's not typed in. You could have a system where you have to type in the MAC address of the router, but that's not how it's done. You type in the IP address of the router, and it finds the MAC address dynamically. So it says, who has this? Tell me. Then it'll get an ARP reply telling you the MAC address. And this is a problem because that process doesn't have a time limit, it doesn't have a password, it doesn't have encryption, so you can lie and trick devices into sending traffic to the wrong place. So anyway, this is used to find the MAC address on the LAN. There was an earlier thing called reverse address resolution protocol you could use to deliver IP addresses to devices like DHCP. And so if I want to find the gateway, I say who has it, and then I get an answer. Tell me where the MAC address is. Now I know where to send my traffic to get to the internet. So I can have an attacker that listens for requests and then lies and tricks you into believing it's the router. It can then forward it like a router, and now it's in a privileged position or a man in the middle. It's in the middle of your traffic. Now, if your traffic is encrypted with a good protocol like HTTPS, they won't be able to do much of anything from here because they can't read or modify the traffic. But if you're using an unencrypted protocol, they can now read it and modify it. Unicast traffic is by far the most common, one sender to one receiver. Multicast is one sender to several receivers. And this is rare on the internet. It's mostly used by routing protocols to send things like routing updates to the other routers on a network, not usually used by end users. Broadcast traffic is one sender to every device in the network. You can do this limited broadcast of all ones in the IP address, and that will send a layer 2 broadcast to the MAC address that's all ones, and that will just send to every device it can reach on a local network, everything connected to the same switch or hub. There used to be something called directed broadcast, where you could be far away on the internet and send traffic which would then go to every device on a foreign network, but this was used to amplify DDoS attacks. I could send a single ping to a network. I'd then get thousands of ping replies, and I could forge the from address. So those go to somebody else, so I hit somebody else with a DDoS. That was called a Smurf attack, and so now they block these. You can't, this directed broadcast won't work anymore. If you try to send something over the internet, hit a broadcast at the other end, it will refuse to forward the packet. All right, then there's promiscuous mode, as I mentioned. In promiscuous mode, your network card listens for every possible frame it gets on the wire. Now, if you're on a modern network with a switch, there probably is no traffic on the wire except what's aimed at you, so it won't make a difference. But if you're on a wireless network or a network with a hub, then you get a lot of traffic coming in that's really intended for other people. And you might want to sniff on that. And so you need this for network intrusion detection systems, that's the game here. All right. So there's OSI layer 4, TCP. You got the source port, the destination port, the sequence and acknowledgement number to label the order of the packet so you can reassemble large blocks of data. And then you got flags like SYN and ACK and push and such, and then various other things there. So you got the well-known ports is the official term for the first 1,024 of them. You need root privileges to listen on these ports on a operating system like Windows or Linux. And they're called reserved ports because they're for the really important protocols that people use all the time, like HTTP and HTTPS. The other ports are considered ephemeral ports. Anybody can listen on them. They're typically used for the client end of a connection that's only used during the duration of that connection and then thrown away. That's what's ephemeral about them. A socket is a combination of 4 numbers. So if I connect from one on each, the server, well, here's the client end, here's the server end. So I'm making an SSH connection on port 22 to this server. So here's the server's IP address and the server's port, which is 22. The client has an IP address, and the client will just pick a large high-numbered port, like 51.178 to be their end. And these 4 numbers together are called a socket. And now the 2 devices can communicate to each other with the traffic being sorted so they doesn't get mixed with anybody else's traffic. It's like I had a cable dedicated just for my client to talk to that server. All right. Doesn't imply any encryption or privacy. It just means that the packets are correctly sorted, so my client application will talk to that server application. All right, so you can have a state of listening. You're waiting for a SYN. Established means the handshake is complete, and there are some temporary states it goes through during the TCP handshake, SYN, SYNACK, ACK. So here's some flags. The most common I mentioned is SYN and ACK. You need those for every handshake. Reset ends a connection, saying the user has closed the browser, they don't want to talk to you anymore. Finish is another way to end it. There are some more flags added. All right, so here's the TCP handshake. You send a SYN. The server replies with SYN-ACK, you send with ACK. You have to do these 3-way handshake before you can send data either way. So this is what establishes the connection. This is why TCP is more reliable than UDP. UDP, you just send the data, you don't know or care whether it got there. In TCP, you make sure the server's listening and ready first. Just like when you make a phone call, you say hello, they say hello, now you can talk because you know there is in fact somebody at the other end for you to talk to. All right. Anyway, let me turn this thing on. All right, so, all right, then the UDP, like I say, no handshake, no acknowledgements. There are port numbers, but you just send data. There's almost nothing else to it because there's no handshake. You don't even know if the other device at the other end is turned on. You don't care. You're like a broadcast AM station. You're just sending out data with complete disregard for whether anybody's listening or not. All right, so 4C is here. Keep adding more little figures every time. Right, no class tomorrow. It's a day of meetings. I think we're required to do this for state law. Supposedly teacher training. That's right. The post office is shut, the banks are shut, but we aren't. Yeah, nobody knows why things happen around here. All right. So what kind of transmission uses that address? 4255. Yep, that's a broadcast. It will just go to every device it can physically reach. That's what you do when you're looking for an IP address when you first boot up. You broadcast, hey, is somebody out there a DHCP server to give me an address? Switch ports require administrative privileges to listen on. The first 1024 ports, those are the ones that are for famous services. These are for less important things like games and stuff. All right, what flag is used to initiate a connection? SYN. You send a SYN, then hopefully the server will apply with a SYN-ACK. All right. Oh, not done yet, okay. All right, what UDP flag initiates a connection? Nothing. It's a connectionless protocol. You do not have a handshake. There's nothing like that. You just spew data out on the wire, and you never even know if anybody's listening or not. That's UDP. All right, Space Invader wins again. Looks like the same three people. And so it is. All right, it's about 10 minutes to 7. Let's take a break until 7. I'm going to stop this recording